Unit 2, Homework 1. So I do expect that you're going to have a different order of questions. I also expect that you will have different numbers associated with your questions. So I will show you the method, but you still need to plug in your values in order to get your correct answer. So my number 1 has a solution of weak acid HA at equilibrium. So it would be at equilibrium with its parts, hydrogen and its conjugate base. And we're told that we have this concentration of weak acid, 0.120 capital M molar. It has a pH of 2.53. So calculate the pKa of the acid. So this is an example of a problem that expects you to understand not only what is a weak acid at equilibrium with, but how is that related to the Ka? And how do you calculate the hydrogen ion concentration from a pH? Now, the pH equation is pH equals the negative log log of the hydrogen ion concentration. So to put this into use here, I need a 2.53 here, but how do we get the H positive? How do we get that hydrogen ion concentration basically out of the equation? You need to use your anti-log, and it probably looks like a 10 and then has a box. It could be 10 raised to the x power. On my calculator, it is shift and then the log log button. Now, you do have to bring that negative sign over. So what you're taking the anti-log of is the negative 2.53. So the negative pH will end up giving you the hydrogen ion concentration. Now, when I do that in my calculator with these conditions, so a pH of 2.53, I get the hydrogen ion concentration as 2.95 times 10 to the negative third. Now, we are told this is at equilibrium, and if you have your particular homework set doesn't have the words at equilibrium, then you need to mentally insert it, because I did make that change, but I believe some of you had already opened your homework. So this is your hydrogen ion concentration, but stoichiometrically speaking, this is also going to be your concentration of weak acid. So in order to find the Ka of this solution, then, you need to take the concentration of the hydrogen ion, multiply it by the concentration of the conjugate base, the anion, and then divide it by the concentration of the weak acid at equilibrium. So this value is inserted for both of these concentrations. Then I get a Ka value of 7.258, and again, I have plenty more digits, but they're just going to stay in my calculator. So this is the Ka value that I get. To take the pKa value, I need to take the log log of this number. And it is, of course, the negative log log, so I need this pKa for my situation is 4.14. So because this is an exponent problem, it's just formatted strangely. So 4.14, and that would be 10 to the 0. Number 2, my number 2 is at what pH will calcium hydroxide precipitate when a 2.245 molar calcium solution is treated with sodium hydroxide. So we have our calcium hydroxide, and we will have some form of an equilibrium. We have a KSP, so it will very heavily lean towards the solid itself, but we will form calcium ions and 2 hydroxide ions. Now we have for our KSP is going to be formed by the concentration of the calcium ion times the concentration of the hydroxide ion squared. We don't know the concentration of the hydroxide ion, but we do know the concentration of our calcium ion, 2.245 in my problem, and we have the KSP, 5.02 times 10 to the negative 6. So we can calculate that concentration of the hydroxide ion by taking 5.02 times 10 to the negative 6, dividing it by 2.245. So this value, this 2.236, and I get more digits, but that's okay, it's going to stay in my calculator. This is equal to the concentration of the hydroxide ion squared. Now we need to take the square root of that value. So the concentration of my hydroxide ion is then 1.495, and this stays in my calculator, times 10 to the negative third, capital M molar. So it is my preference when I have a hydroxide concentration in my calculator to just take the log of that value, because that gives me the pOH. And the pOH here is 2.825. Again, it's going to stay in my calculator. And then it's pretty easy to calculate the pH, because the pH is going to be equal to 14 minus the pOH. So then I have a pH value of 11.17 for my conditions. Number 3, I'm going to find the pH of a solution that has a hydrogen ion concentration. So I'm told the hydrogen ion concentration of 2.33 times 10 to the negative 8. Ignore the double negative there. I'm not sure what's going on. But 2.33 times 10 to the negative 8, capital M molar. So to find the pH of a solution, we need to take the negative log log of the hydrogen ion concentration. So I punch in my calculator, I hit log first. In your calculator, you also may hit log first, but you may have to punch in your number first and then hit log. This is to be entered in scientific notation, so be sure you're using your exponent key or your EE key. If you are not, and you are actually punching 2.33 and then the multiplication sign and then 10 and raising it to a power, you need to make sure that this whole number is in parentheses so that your calculator knows you're not just taking the log of 2.33 and then multiplying it by this exponent, okay? Make sure you understand how to use your calculator. If you don't or you have questions, please reach out. I am happy to help. Just send me a picture of your calculator and I will tell you what your keystrokes are. So you pop that into your calculator, and the pH then is the negative log of this value. I get 7.63. So 7.63, and actually, well, Harris is inconsistent with how many significant digits we would use in a log. Noting the characteristic and the mantissa, it would actually be 6.33, but Harris then goes on to say later that we usually round to the hundredths place. I'm not going to count you wrong if you just put in the hundredths place here. Number 4, explain how metals with a charge of 2+ or greater act as weak acids. Well, this is part of the lecture portion, or the written out portion that is actually in the classroom. So your metals end up being solvated, and because they are solvated, they create a coordination bond that holds water molecules around those ions of 2+ or greater. So the metal acts as a Lewis acid and accepts the electrons from the water. That also opens up all of those solvated water molecules to end up being Lewis acids as well. Not Lewis acids, Bronsted-Lowry acids. And another water molecule can come in and pull that extra hydrogen off because oxygen would rather not have that positive charge. So something along those lines for the explanation for number 4. You can expect to see that one on a quiz, so make sure that you do understand that concept. And number 5, we're going to place these acids in base examples in order from the most acidic to least acidic based on the pKa values. So the lower the pKa, the more acidic it is. So hydrochloric acid with a pKa of -6 is going to be the most acidic, followed by sulfuric acid. And then we will have, this one is 3. I'm looking in order, so I'm going up from the smallest number to the largest number, 2.87, and then this one would be 4. Here's 5, and here's 6. Please reach out with any questions. I am happy to help you.